Now I'm going to explain why Lagrange's theorem is true. What's the proof? We saw an intuitive idea when we drew tangent contour lines and parallel gradient vectors, but it's really important and interesting to look a little more closely at it. So here's a reiteration of the statement of Lagrange's theorem. We have a critical point on a level curve g of xy equals k, and the gradient is not zero. Then that means that the gradient of the objective function is parallel to the gradient of the constraint function. So here's how you can prove it. You take a parametrization of the constraint. So the constraint curve is a curve, and we can do a parametrized curve, which we saw in the previous chapter of the Stewart book. We looked at parametrized curves, and let's call that R of t. And this R of t goes along the curve. It goes through point P. So let's say that P is R of something. Well, let's just say t0, just to some value. This is some particular initial time or whatever when it goes through that point on its way along the curve. And now, and a technicality here. This parametrization exists. The parametrization exists as long as we know the gradient of g is not equal to 0. How do you know it exists? We were given an equation, and so to convert from an equation to a parametrization, it turns out that's always possible. You can always take an equation-defined curve and rewrite it as a parametrization, and that is called the implicit function theorem. So that's just part of the technical underpinnings that give us a guarantee that we can do this maneuver of converting an equation into a parameterization. If you're curious about that kind of thing, you will learn about implicit function theorem if you take a class in real analysis, which at Boise State would be Math 314 and 414. Well, more so in 414, they'll talk about the implicit function theorem if you're curious about that. It's kind of a fun story, but for right now, it's a bit of a supporting role. It just lets us say that this R of t does exist and we can use it. Okay, so anyway, long story short, we have a parameterization R of t. Now what we want to consider is we want to consider f of R of t. Well, and g of R of t. All right, so let's start with g of R of t. What's g of R of t? Well, it equals k. It's constant because we're following the curve where g equals k. At all these points, g of these points equals k. So that means that the derivative of this is 0. But what's that derivative of g of R of t? That is the chain rule for paths. So we get that the gradient of g at this point P dotted with the derivative r prime of t is 0. So in other words, the gradient of g is perpendicular to r prime of t. Okay, well, now let's look at the other one, f of r of t. That is not a constant function. The value of f goes up and down as we trace along this curve. But what we do know is that this p is a critical point. P is a critical point, and that tells us that the derivative of f of r of t, well, I don't know if it equals 0 in general, but I do know that at point P it equals 0. The first one was just equal to 0 in general, but this one is equal to 0 for that one point. Well, let's do chain rule for paths again. So the gradient of f at that one point, dotted with r prime of t. Oh, I should have said t0. T0 is the relevant t value for point P. And it's the same t0 for both of them. So I should have said t0. Anyway, that dot product is also 0 because that's what the chain rule for paths does. We're just using the chain rule for paths again. Okay, so the gradient of f is perpendicular to r prime of t0. All right, so the gradient of g was perpendicular to r prime of t0 because this is a constant function and it has derivative 0. The gradient of f is perpendicular to r prime of t0 because this isn't a constant function, it's just that it has a critical point, and critical points are where the derivative equals 0. All right, so each one for its separate reason is perpendicular to the same vector. Okay, so the gradient of f and the gradient of g are perpendicular to the same vector. Here's r prime, and these other two vectors are perpendicular to it. That means that they have to be parallel. They have to point in the same direction. And that's it. That's the reason why Lagrange's theorem is true. I really wanted to emphasize how the chain rule for paths plays a key role in this proof.